Recording a test, recording a test. All right, welcome to this video where I will be discussing turbulent flow in a channel. And the idea behind this discussion is that we're going to talk about the velocity distribution that you get when we have turbulent flow in a channel and the friction factor for that turbulent flow in a channel. So I'm going to be working off of a PDF, which is I have tried to distill down everything we need to know in order to get a reasonable estimate of the velocity distribution and the friction factor for turbulent flow in channels. In this case, we're considering a circular tube at steady state, fully developed, and on horizontal configuration. So what happens is when the flow enters a tube, you will see a flat velocity distribution at the beginning, but then due to friction with the wall, just as in laminar, the fluid can't slide over the wall, so the friction at the wall causes the velocity to be zero at the very edge where it contacts the wall. And then the difference we've seen between turbulent flow and laminar flow is that in turbulent flow we have a rather flat velocity distribution across the center of the channel. And then we have a relatively short drop from the middle of the flow, which is relatively constant in velocity, to the flow near the wall, which goes down to zero on both sides. And the reason we see this relatively flat velocity in the middle is because we now have fluctuations in the velocity, so we don't have a smooth flow. What we have is a flow condition where we have some velocity, some bits of fluid flowing a little bit faster than other bits of fluid right next to it. So we add this fluctuation term to the average velocity. So we have an average velocity plus the fluctuation gives you the local velocity at any moment in time. So if you use that idea and rewrite our momentum equation, our conservation momentum equation, we have that the acceleration, the bulk acceleration for the flow plus the flow acceleration due to velocity changes, where we have this average velocity here, equals the negative of the pressure gradient plus a shear stress term, which now is going to include the concept of this velocity fluctuation, and gravity, which we are going to say is zero in this case. So if we look at the shear stresses now, we can't just replace this shear stress with a simple viscosity times the gradient of the velocity as we did in laminar flow. What we have here is the shear stress itself, which is still defined as mu times the grad v, but we have to account for the fact that there is fluctuating flow around the fluid, giving us an overall effective viscosity that's a little bit lower. So we take the tau effective in the flow direction. It's going to have a component due to velocity in the z direction being affected by flow in the r direction, and vice versa, flow in the r direction being affected in the z direction, because of this tensor where we have flow in three possible directions, z, r, and theta, and then surfaces normal to each of those three directions. So that'll give us 9 total possible. We're just talking about one of those components right here. So what we end up with is our normal viscosity and something due to the fluctuations in the velocity, which are represented by this term here, this epsilon m, which is the momentum diffusivity. And that is related to how well those little changes in the packets of fluid are able to transfer their momentum to each other. So, in a turbulent velocity distribution, we have to solve this equation in order to develop the velocity distribution, and that is very difficult. So to derive the velocity profile from first principles, when we have this kind of fluctuation added in, or this perturbation added in, makes it not worth our while to investigate for the purposes that we're looking at here, where we're going to look at flow in a nuclear reactor's core up the fuel rods. It's easier to use correlations that have been developed from experiment, which are those experiments having been developed for the conditions relative to relevant to the reactor case. And what we'll see is that the actual velocity distribution, based on these experiments and the correlations that model them, is relatively flat in the middle again, but it has several layers. So there's a laminar sublayer near the wall. That's because flow near the wall is slowed down due to the friction with the wall, and slow flow is laminar flow. So near the wall we have a laminar sublayer. Near the middle section we can take full advantage of these fluctuations, transferring momentum in order to keep things relatively even across the middle. And then in between the laminar sublayer near the wall and the turbulent core in the center of the tube flow, we have a transition layer where energy is transferred in and out of the turbulent layer and the laminar sublayer, but not in a regular pattern. So that gives us these three cores, and we're going to use a geometry to try to define some equations that can model this shape of this velocity profile, where y will be our coordinate we're going to use, y being 0 at the wall and going up towards 0, up towards the radius of the tube at the center. And that's a little bit different than you would normally see, where we go in the coordinate r being 0 at the center and out towards the radius at the edge of the tube. And then we're going to make two definitions. We're going to have our z velocity plus and our y coordinate plus defined as our actual z velocity divided by the square root of the wall shear stress divided by the density. So we have an adjustment factor on our velocity here to give us Vz plus, and an adjustment factor on our y coordinate, again using the square root of the wall pressure over the density, and then dividing by the kinematic viscosity as well here. So our regular y coordinate is multiplied by the square root of the shear stress over the density and divided by the kinematic viscosity, where kinematic viscosity is regular viscosity divided by density, in order to get our units to work out here. You may remember from a prior video that the definition of the friction factor and its relationship to the shear stress at the wall being in the laminar sublayer, we're going to have the same relationship we saw before in terms of wall shear stress over here, because at the wall we have the laminar sublayer. So we have the same definition for tau wall being related to the friction factor at the wall. So with these definitions of Vz plus an adjusted velocity and y plus an adjusted coordinate going from the wall to the center of the tube, we can take the experimental results and say that we can have three equations that will give us our velocity profile in the three sections of the tube: the laminar sublayer, the transition layer, and the turbulent layer. So in the laminar layer, we'll say that Vz plus equals y plus. Very simple calculation. And then in the transition layer, our adjusted velocity is minus 3.05 plus 5 times the natural log of y plus. And then out in the regular turbulent layer in the turbulent core in the center of the flow, we have our adjusted velocity equals 5.5 plus 2.5 times the natural log of y plus. So if we are plotting our velocity profile in terms of Vz plus and y plus, these are easy coordinates to plot. You can easily run these in Excel and just vary y plus, where y plus goes from 0 to 5, calculate it, Vc plus is equal. Then vary y plus from 5 to 30, and calculate Vz plus with this middle equation, and then vary y plus from 30 and up until you get to the center of the tube, given this equation over here. And you'll plug in those y plus values from 30 to the center of the tube to get Vz plus in the core, turbulent core. If you want to combine these all into one equation, that would fit it a little bit better. That's what Reichert did. So these three zones being modeled independently is the Martinelli model. These three zones being combined in one equation that is derived to fit them fairly well. You have Reichert saying your modified velocity is equal to 5.5 plus 2.5 times the natural log of your y plus coordinate times this ratio involving the size and relative position of the tube, where you have your position in the tube r, which is our normal coordinate r going from the center out, r goes from the center out, and then the radius of the tube. We're going to use Martinelli for the homework problem in our class. So, this is the correlation that is modeling the situation with this theoretical application of the conservation of momentum being satisfied, where we're accounting for velocity fluctuations. Those velocity fluctuations are represented through an adjusted shear stress, causing the turbulent core to be relatively flat. Okay, so our velocity profile is there. We have our three terms. And I should note here, if you want to plot not Vz plus versus y plus, but actual velocity Vz versus actual position on the tube y, you need to solve this equation here for Vz and solve this equation here for y in terms of Vz plus and y plus. So you can calculate Vz plus at every position y plus. Then, for those positions y plus, solve for y, and for those modified velocities Vz plus, solve for Vz. And that way, you're plotting the actual velocity Vz versus the actual position in the tube y. Okay, let's move on to the friction factor. If we wanted to work at the turbulent friction factor, we're going to again use correlations. The derivations are just too hard. We've already given up here on trying to find a method for finding a velocity profile that comes from first principles. So in laminar flow, we used a velocity profile that was derived from first principles in order to find our friction factor. In this case, we already have a correlation for our velocity profile, so we're also going to use correlations for the friction factor. And we just calculate it based on the Reynolds number and then some coefficients. So we're going to have a coefficient out front times some Reynolds number raised to a power, giving us a friction factor for different conditions. So if our Reynolds number is sufficiently small, being less than 30,000, then we can use this Blasius definition for the friction factor. But if our Reynolds number is fairly large, between 30,000 and a million, then we want to use the McAdams correlation for the friction factor, which has a different coefficient and a different power on the Reynolds number. I'll just note here that these Reynolds numbers, 30,000 and a million, are very large compared to the limit for the Reynolds number for laminar flow, which is about 2,000. So if we had a Reynolds number that was, say, 2,000 here, we would not use Blasius. We would use laminar flow. And if we had a Reynolds number that was somewhere between 2,000 and 3,000, we could try to use Blasius, we could try to use the laminar, but the real answer is probably going to be somewhere in between for what the friction factor would look like. So those are the answers for smooth pipes. We use Blasius and McAdams. If we have rough pipes, which is not an analogy that's useful for a nuclear reactor core, because the fluid, the coolant that's flowing up along the fuel pins is flowing on smooth surfaces. But if we didn't have a smooth surface, say we had a damaged surface, then our friction factor will be found from the Moody chart, where the roughness of the pipe is found from experiment on the pipe itself, and the Reynolds number for the flow is calculated given the flow conditions, and then we use that combination of how rough the pipe is and our Reynolds number in order to find out. Like I said, that's not going to apply in our particular class. So, the reason, as we did in laminar flow, to find the friction factor is so that we can calculate the pressure drop. And we need to know the pressure drop because we need to know how much pumping power is required to keep the fluid flowing in our piping system. And we need to know how much pumping power so we can buy the right pump and run it at the right speed to move our flow. So, as in laminar flow, our pressure drop is the friction factor times the length of the pipe over its diameter times the density times the average velocity squared over 2. No different in the turbulent case here. Our Reynolds number is defined in the same way. So the key here, the difference here, is finding the friction factor in the turbulent case in a different way than we did for the laminar case. And then I just note that we've been considering only fully developed flow. So the actual entrance to the nuclear reactor's core, where the fluid first starts to flow up the fuel pins, will not be fully developed. However, that distance is fairly short. We typically do have a turbulent flow in the nuclear reactor's core, and we're going to be arriving at fully developed flow somewhere between 25 and 40 centimeters, given the diameter of our tubes is about a centimeter. So fairly short distance compared to the multi-meter length of the fuel pins. And that's it. That is what we need in order to that is what we need for our turbulent velocity profile and pressure drop. Thanks.